he couldn't imagine a world where you could be locked inside of a boat or a spaceship or a car or anything going constant velocity and being able to do any kind of experiment where you would be able to determine that you're moving or not. That did not make sense to Einstein at all. And everything that we know about light wasn't known back in the time of Galileo. So Einstein was trying to figure out a way to fit light into the equation, and this is what he came up with. He also concluded that the existence of the ether was not necessary for this theory either. So how do we make all of this work? We re-examine the equation speed equals distance over time, because that's what speed is. If I'm going 40 miles per hour and I'm outside for a full hour, then I've gone 40 miles. If I'm going 40 miles per hour and I'm only driving a half an hour, then I've gone 20 miles. So I can plug anything into the equation and get a speed out of it. Okay? We anticipate the light beam, like the tennis ball, will cover a different distance for the observers on the train that will for the observers on the ground. In other words, if we go back to our train example, I said if you throw a tennis ball at 15 miles an hour and the train is also moving at 45, the speed really depends on what frame of reference you're in. But remember, Einstein had something special to say about light. What Einstein said about light is it's always going to travel with the same velocity, unlike the tennis ball. Right? So Einstein said that light, unlike the tennis ball, must always have the same velocity for all observers in order for Galileo's relativity to be kind of updated into the 20th century with all that we know about light. And again, that's so that light remains constant and there isn't anything that you can do to determine whether you are moving at constant velocity. But how can this be? You can simply imagine that tennis ball having different velocities calculated for different observers. I'm standing still, this person's moving with the train. We argue about the different velocity that the tennis ball is going. He's saying, no, it only went 15. I'm saying, no, I saw it go 60. But Einstein's saying, with a beam of light coming out of a flashlight, bouncing this way or that, we're all going to agree that it's going to go exactly 186,000 miles per second. How can this be? Well, he thought about it, and he basically said, Michael Bessa, who's a good friend of Einstein's, who he bounced ideas off of quite frequently, had a discussion with him about this problem, and then he went home and figured it out, and later the next day he talked to Bessa about it, and he said, thank you, I've completely solved the problem. My solution was really for the very concept of time, that is that time is not absolutely defined, but there is an inseparable connection between time and the signal velocity. So essentially what that means is this. Because we have a problem with light that we didn't have with the tennis ball, we have to find some way to compensate for that. And Einstein concluded that time is probably not absolute, even though it would be more comfortable for us to think of it as absolute. Since speed equals distance over time, and that flashlight beam coming out of the flashlight is covering a different distance for the guy on the embankment as opposed to the guy inside of the train, the only way for that speed to maintain at 186,000 miles per second for both parties, even though our distance is different for both parties, is for the time to be different for both parties. So Einstein introduced this concept where, hey, your clock isn't necessarily going to be running at exactly the same rate as my clock if we're traveling different velocities, and later we'll see if we're in different gravitational positions. So this introduced a very comprehensive look at the possibility that time is not absolute, it's actually relative. And we can see this is something that we'd be highly interested in if we want to understand what time is to begin with, right? By the way, I should say that, again, this is, if you remember that equation that we looked at about a minute into this, that was a little bit more complicated with the V's and the C's and that sort of thing, would be the real equation that Einstein would have used to determine the different distances and the times and all of that. I'm just keeping it very simple for the sake of argument, but conceptually it works the same way. Well, the rate at which a clock ticks is relative to its velocity. So that's what Einstein is saying. If we were in a train that could move at 9/10 the speed of light, we don't have any. We do have high-speed rails, but nothing that fast. But if you're in a train that could move 9/10 the speed of light, and somebody was standing on the embankment while that train was whizzing by, then we would have two people in two very different reference frames. One would be in a very fast-moving constant velocity reference frame, and the other one would be standing on Earth completely still. But remember, to interpret Galileo's principle to the letter of the law, while that person is whizzing down the train track at constant velocity, he can assume that that person and the entire planet Earth is whizzing by him, and he's the one who's standing still should he look out the window, right? If there are two stationary clocks at point A and point B, and the clocks are synchronized, and the clock at point A moves to the clock at point B at velocity v, upon its arrival at point B, the clock will no longer be in sync. The clocks will no longer be in sync. The clock in motion A will be lagging behind the stationary clock B, right? And so clock A moves to clock B. George Lucas wasn't available for the special effects, so that's pretty much what you're going to get. But the point is that, and this is right out of Einstein's paper from 1905, where he discusses this aspect of special relativity and how it has an effect, the motion has an effect on time. Again, these two clocks start out in sync. They're ticking at the same rate, so they're in sync. So right now they're both saying high noon, but this clock moves with a very fast velocity that we'll say. And then the consequence of its velocity actually causes its clock to slow down during that time period. So then when it unites with clock B and they compare notes, clock B says, well, my watch reads, 12:02 and 30 seconds. Clock A says, well, geez, my clock still reads 12:01 and 53 seconds. So clock A is lagging behind because during that time period that he was in motion, his clock was running slower than clock B's. Right? So that brings us to the twin paradox. And we're particularly interested in the twin paradox during the study of Einstein's relativity because, again, because of the time factor. We're very interested in seeing if we can determine if there's any kind of mechanism, any kind of root cause for why this velocity change has now caused time to slow down for clock A. But we do have a problem because if we do follow Galileo to the letter of the law, if all motion is relative, then how do we explain why clock A ran slower than clock B during the period of relative motion? Again, taking it word for word right out of Einstein's 1905 paper, he committed to clock A slowing down so that when clock A and clock B united, their clocks were no longer running, they weren't set at exactly the same time. Clock A was running behind clock B. And the question is, well, why didn't it happen the other way around? Right? Einstein's answer to that is actually acceleration. And there's an interesting history behind that. This explanation has actually been subject to many different interpretations since its development in 1918. But it's caused a lot of confusion between 1905 and 1918, and even from 1918 up until now. There's a lot of people out there that will say, well, Einstein's relativity is something that is pretty much cast in stone. It might be complicated, it might take time to learn, but there doesn't appear to be any room for discussion with regard to what it says and what it predicts and how it predicts things. But yet, in spite of that, if you really analyze the facts, you will find out that there really isn't a consensus on how or why these things came to be. I'm going to give you an example. On the acceleration, and I'm going to go over to the board here, I'm going to kind of draw how I viewed things when I was first learning relativity. So we have clock A and clock B here, and clock A decides to go for a ride. And for most of the trip, clock A is traveling at constant velocity. But Einstein says that the acceleration actually has something to do with why we can commit to A's clock slowing down and B's not running slower during that same time period. In other words, A was actually sped up, and at some point A was actually slowed down, where nothing happened with B's clock. So A experienced something that B did not experience. Problem with that, if you think about it though, is You'll see some acceleration in the beginning when it goes from 0 to whatever, 9/10 the speed of light. You'll see some deceleration. It will slow down when it actually slows down and turns around. Of course, it'll reaccelerate to some constant velocity. And then finally, it'll slow down again when it goes from whatever velocity to coming to a stop here, okay? The problem is most of this journey in this particular diagram, we would show as being constant velocity, say from here to here. Well, what happened? During that constant velocity is A, which is the moving clock, does it carry some sort of memory that in a previous period of time that it experienced an acceleration? Because supposedly all of the things are happening, or most of the things are happening while it's in this state of high velocity, but yet it's constant velocity and relative motion, but yet it experienced acceleration at a previous time period, right? And when it experienced this acceleration at a previous time period, that somehow had an effect on what's happening during this constant velocity. So that was something that puzzled me for years and years and years. And it wasn't until, I'd say, 2007 that I did more research on this and actually found out what the various interpretations were that were out there that are available. You know, some look good, some don't make quite as much sense, but at least it kind of answered this conundrum, this dilemma here. Although the theory of relativity has been widely accepted for decades, there's not been a consensus among physicists on how to resolve this twin paradox issue. Again, A's clock is the one that accelerates. It has a time period where it's constant velocity, turns around, has constant velocity again, and then it slows down and comes for a landing back on Earth, reunites with B, and again, B looks at his watch and says, it's 3:15 here, and A says, well, geez, my clock only reads 2 o'clock, so something happened, and they're attributing it to something that happened with A that B did not experience. And we have to come up with some sort of step-by-step explanation for all of that. And that's really, you know, we're interested in that because this is time slowing down. And if we can actually come to a real reason why time has been affected in this way, we might be able to determine what time itself really is. But what doesn't help is there is no consensus, even among the experts, on what has happened here. The first expert we're going to talk about here is John Archibald Wheeler and Edwin Taylor. They wrote a book called Space-Time Physics. Wheeler is probably one of the most highly regarded physicists of all time. He was advisor to Nobel Prize-winning Richard Feynman, a number of accomplishments with general relativity, gravitation, that sort of thing. So a very, very well-respected physicist and somebody who was very, very familiar with the ins and outs of relativity, to be sure. They address this twin paradox by asking the question, do we need general relativity to answer this paradox question, which we'll get into more detail in a second. And they quickly answer no. They further sum up the paradox by saying, there is never any contradiction between a single clock in one frame and a single clock in any other frame. In this case, special relativity can do the job just fine. In other words, we're using special relativity for the entirety of this journey to somehow explain why A's clock can still legitimately slow down where B's does not. Okay. We have explanation number 2. Nobel Prize-winning physicist Max Born had a lot of contributions. He wrote an entire book on relativity, which encompassed special theory, general theory. Also did a lot of work with quantum mechanics. In any event, here's what he said about resolving this paradox. The clock paradox is due to a false application of the special theory of relativity, namely to a case in which the methods of general relativity should be applied. So we got a problem here, because I want to learn more about relativity so that I can maybe learn a little bit more about time, and so I'm looking for the official reason why, or the official explanation within the confines of relativity for why things are happening with these clocks, and there doesn't appear to be one definitive reason among the experts. Again, as we can see if we back up here, Wheeler and Taylor say special relativity can do the job just fine, and Born says just the opposite. He says general relativity should be applied, and it's a false application of special theory of relativity. Yet another take here. This is something that